before the last lecture today, let me make an announcement about tomorrow's excursion. So let me introduce Professor Greg Mckenna, well known for the polymer rheology and he'll talk about structural recovery.
This is, I'm an experimentalist, and I'm going to talk about experimental results for the most part. And I think that this is very important because, in fact, this is what we might call a reality check on all the theories we've been seeing. And so I think it's important to keep it in mind. And before I do that, though, I think most people don't know where Lubbock, Texas is, so I thought I would show you. Here's North America, and down here is Texas, and Lubbock is somewhere up in there. Close in, Google Earth is great, isn't it? Close in, here's Dallas, people have heard of, and over here is Albuquerque, New Mexico. And if we come in closer, what we see is Lubbock is 500 kilometers to the west of Dallas. Another 500 kilometers is Albuquerque, and Lubbock's the biggest thing in between. Okay, so about 220,000 people. I mean, that's a little village here, right? Maybe a really little village, right? And but I do like to point out we're up on the high plains of West Texas, but people worry about if it's too dry. I like to point out we have grass, we have flowers, and we have trees. And we think that at this university of about 30,000 students, at least in chemical engineering, it looks like they're having some fun doing their polymer and glassy behavior research, okay? Okay, so that's our introduction to Lubbock. Now, what I'm going to do is first I'm going to kind of give you an outline, some background first about the glass transition, just to show that, in fact, what people have been talking about is really a simplified picture of the glass transition, because what we really observe in the laboratory is a very complicated phenomenon. And then I'm going to specifically talk about the temperature jump experiment so that we see what we're talking about. And Kovacs categorized several types of experiment that really have to be reproduced by theory if you're going to be able to really understand the glassy behavior. Not the formation of the glass per se, but the behavior in the glassy state as the glass approaches equilibrium in different ways. And then I'm going to talk about the two phenomenological models that are most commonly used to talk about structural recovery. And that's the so-called Toole-Narayanaswamy-Moynihan and the Kovacs, Aklonis, Hutchinson, and Ramos models. So the TNM or the KAHR model. And then what I'm going to do is, after I do that, then I'm going to talk about some actually maybe anomalous results that's worth thinking about, where because polymers provide a certain kind of versatility to do experiments, it turns out we were able to do chemical activity jumps, meaning changing concentration of plasticizer, either relative humidity or carbon dioxide, and watch the behavior in a way that shows actually some surprising results about the glass transition itself, or the glassy state itself. And then I'm also going to talk about how well these models describe the actual structural recovery of a material confined in nanopores. Okay? So I like to make a point of the fact that we've been talking about the glass transition quite often, although like the last talk did not make it a point. But the glass transition temperature is not a temperature. It's something that's path and measurement method dependent. So depending on exactly what you do, the actual value you report for the glass transition temperature is going to be different. So part of this is because of the kinetics. Part of it is perhaps because of the path dependence itself. So that's something we have to be concerned about. And it's also important then when you try and define certain things like maybe a Prigogine to Fay ratio or something like that, to realize that this is a kinetic phenomenon, not, at least as we measure it in the laboratory, not a thermodynamic phenomenon. So the path dependence, well, the easiest thing to see is, this is some data from Kovacs. And the glass transition depends on rate or time. So this is a plot of the specific volume as a function of temperature for a polymer, and I think it was polyvinyl acetate. But we start from the, well, in that material, we don't have a crystalline state, so we don't have a supercooled state. It's an equilibrium liquid state. Okay, but it would be equivalent in some of your glass formers to the supercooled liquid state. And what we see is as we cool the sample, of course, at some point we get a departure of the material from the equilibrium line, which is this line, and that point we call the glass transition temperature. And what Kovacs showed was that, of course, if you change the speed at which you do this, and this is actually each data point represents a jump that takes 0.02 hours. In this one, each data point was 100 hours apart. Okay, so these are very long experiments, right? Something to keep in mind as you worry about doing your computer simulations. Here was somebody doing experiments. Each one of these data points represents waiting 100 hours. Okay, so a little bit of patience, you know. So, but the thing is that what we see is that the TG depends on how fast I went. And in the case of polymers, this dependence is about maybe 3 to 5 degrees Kelvin per logarithmic decade of cooling rate. And then we see this sort of classic signature in the coefficient of thermal expansion for one of these curves, which makes it look like it's sort of a thermodynamic transition of second order. Okay, but I think the important thing is it depends on rate or time, and this curve would shift if I plotted the slower experiment. I would obviously get a shift to lower temperatures when I plotted that slope, that derivative. Here's another example. This is from Mckenna and Goldstein, and this shows the path dependence of TG and the pressure effects on TG. So, of course, TG depends on pressure. We saw that. This is a more conventional type of experiment where what you do is you go into the liquid state, and then you change pressure. And so here, then you cool it and watch the glass formation at constant pressure. So that's an isobaric surface. And you can define your glass transition surface from this set of experiments. Of course, this is an equilibrium surface. This won't change with path. This is the glassy surface. And the comparison is made with this one where Mckenna and Goldstein said, well, let's take and form the glass, and then we're going to pressurize it in the glassy state. And we're going to see, is this surface the same as this surface? And is the glass line, the one that we're going to be interested in, is the glass line as a function of pressure the same in the two cases? Okay. Well, the next figure shows that indeed it's not. In fact, we see that there's a factor of about 2 difference in the slopes depending on exactly what path I took to create my glass, how I create my glass surface. Okay, so that's already important because that tells me if, for example, I need the derivative of the transition with pressure, well, you better know how you measured it because this factor 2 is quite large. I'm sorry? This is TG here, and this is pressure here. I'm sorry. Yeah, TG versus pressure. And so what we find is that, yeah. I'm sorry. Okay, this is actually the constant formation pressure glass, or variable pressure formation glass, or what they did is they formed the glass here. That the top curve is this curve, this type of curve, and the bottom curve is this type of curve where they formed the glass and then depressurized it. Okay, so in one case, in the middle curve is this kind of surface. Okay, so just as the way you construct the two surfaces. And, I'm sorry? Okay, here you pressurize in the liquid state, and at each pressure cool isobarically. Here they pressurize in the case of the P0, what he called in this one P and 0, that corresponds to this one. Okay, and then you pressurize. And he also had one where he formed it here and then depressurized. Okay. I'm sorry? Those are the 3 curves. Yeah, those are the 3 curves, right? But the big thing is that's a detail. But the big thing is to realize that, of course, even the apparent strength of the transition in terms of dTg, dP is a function of how you did the experiment. What's what? What's the actual change in the pressure? 800 bars. The total range of pressures is 800 bars. People have now done this at much higher pressures. When you go to process a polymer, you might get to 500 megapascals, right? Not 800 bars. So that's making these cell phones that we make, you know. Okay, another example is, here's an example of, we can make a glass from specific volume temperature experiments, these isobaric measurements. This is a polycarbonate glass, and we see sort of the typical behavior that the TG is a function of pressure. Now, here, it's harder to see. These are isochoric measurements. So we can actually form a glass by changing pressure as a function of temperature, but at constant volume. And these are constant volume lines. You can see here that the strength of the transition is not as strong as in this case. Okay? But I'm just showing that, in fact, then the behavior, obviously, this glassy surface is different from this glassy surface. Okay? So again, this is because, why? Because glasses are non-equilibrium systems. Okay, now another thing that's important, now this is probably not so important to this group, but it is important in general, because if you go down to GE, well, now it's Sabic Plastics, here in, I think they're here in close to Bangalore, they make a whole lot of polycarbonate, you know, and they do a lot of work. And they're going to hand out data sheets. And on those data sheets, they're going to have a thing called the glass transition. And the glass transition is really important because it determines the temperature at which you can use your material. And polymer people are crazy. They try to use their material really close to the glass transition. Like 3/4 or 80% of the glass transition, they use these materials. And so it's important to know that. And there was a book written by Ricky Seiler, edited by him a few years ago. And it's really interesting. They make a comment that the differences in assigned values of TG, so they worry about this as a practical matter. What's the method I should use to tell people what my TG is? That were greater, the differences between the assigned values of TG were greater between measurements for a given thermomechanical history than between thermomechanical histories for a given measurement. So, so the formation behavior of the glass has that 3 to 5 degree difference per, say, logarithmic decade of rate. But in fact, when you do something like compare my DSC TG with the TG determined by a dynamic mechanical measurement, they're going to be quite different, and actually they can be quite complicated in some systems. This is a TG plot versus weight fraction of a polymer blend, and here we see the circles are differential scanning calorimetry. The upside down triangles are some sort of dynamic mechanical measurement. And you can see even with the different dynamic mechanical measurements, you get different results. I don't know which one was tangent delta and which one was G double prime, but they're different. And then there's dielectric measurements, and dielectric measurements in this particular instance are even non-monotonic, or not non-monotonic, sigmoidal, as opposed to sort of having a smoothness to the curve. Okay. So it's just an important point. These differences, if somebody reports you the TG here, it's 180 or 190, and down here with this measurement it's below 140. So you can get very big differences. So at least it's something to be aware of as a practical matter. The guy from General Electric's probably telling you this, you know, and what you're interested in is this one, perhaps. Okay, so it's something to be aware of, that the different measurements will actually give you a different estimate of what the TG is. It's not a point in space. It's some really complicated surface, depending on what you're doing.
To what extent is that because of the time scale?
Well, the standard, these are probably all measured at more or less the same time scale. Okay, 1 to 10 degrees per minute. But the dielectric was probably measured at a higher frequency, but it could all be 1 hertz or 10 hertz, right? It doesn't have to be that high a frequency, right? So. But yeah, but the point is just that you can have a difference depending on how you do it, and the details, again, you have to look at. And
sorry, in each case, how is it measured? I mean, how do you say this is TG?
Well, okay, when somebody does a DSC, you know how they do that, right? You get the break in the heat capacity. When you do a dynamic mechanical measurement, there are different estimates of the TG. Some people will measure the peak in tangent delta. Some people will measure the peak in G double prime. Some people will measure the midpoint or some point in the reduction in G prime. okay, as a function of temperature at a scan rate, and at a, it's mixed because you have a scan rate convoluted with an oscillatory frequency, right? And both of those affect what you measure. Okay, so now I'm going to try and talk about structural recovery because that's really what I'm supposed to be talking about. But I did want to point that out because the glass transition phenomenon is quite rich and quite complicated. Okay. And now I'm going to talk about structural recovery today. And structural recovery is what I'm going to call the evolution of the non-equilibrium state or structure of the glass towards equilibrium. So that's what we're talking about today. On Monday, I'm going to then talk about physical aging. And physical aging is the response of the mechanical, and I usually do mechanics, or other property like dielectric behavior to the changing thermodynamic state of the glass. Okay, and we'll see what we mean as we go through this. But the fact is the glass isn't, once we form it, it's not in equilibrium. And then it changes in a way that we want to be able to describe. So glass transition kinetics. So what does it have to explain? So what I mentioned that Kovacs had cataloged this back in the 1960s, and these things weren't original per se to him, but he did a nice job of cataloging the behaviors. And it's what we call the intrinsic isotherms. And the intrinsic isotherms are clearly non-exponential in their response. So we often think of a kWw function. Kovacs thought of sums of exponentials, but it's not a single exponential. Asymmetry of approach, and we'll show what that means, but that shows the nonlinearity of the process, and I'll show what the explanation for that is. And the memory or crossover effect, and that shows the history dependence, and it shows the non-exponentiality. Okay, and I'll tell you what I mean by that. Okay, so here's our sort of what we think of as default figure 1 about the glass, and it's a schematic of either volume or enthalpy versus temperature at a single cooling rate. And this is going to give me the intrinsic isotherm if I do the experiment. So I'm going to take, and the way Kovacs did it, he start off at about Tg, what we think of as Tg. Remember, this thing depends on how I defined it, right? How I did the measurement. But if you start off about here and then jump rapidly in temperature down to, let's say, this point, the material is out of equilibrium and it's going to spontaneously evolve towards equilibrium. And we want to know how it does that. Okay? So that's what we call structural recovery. And this is what Kovacs found. And what he did is he defined a parameter, delta is equal to the current volume minus the volume at infinite time divided by the volume at infinite time. Okay, so if I go back here, that's essentially the distance from here to here, but just normalized by the equilibrium volume, okay? Yeah?
I'm just curious, if you follow the structural recovery, and I mean, can you estimate sort of the additional heat capacity that the system has, and do people make these measurements?
People will also make heat capacity measurements, and I'll show results for heat capacity measurements as well. That would be, people call that enthalpy recovery, and this is going to be, volume recovery is what Kovacs did, but in fact, they're virtually identical. So what Kovacs found was that the volume, and this could be enthalpy, it's just a departure from equilibrium, as a function of the time after the quench, looks like this. So he quenched from 40 degrees to, here's 35 degree as the material ages or comes towards equilibrium. It's pretty quick. As I go down in temperature, these times get longer and longer. So by the time I'm 20 degrees below the glass transition, the nominal glass transition, the time to get into equilibrium is now getting, well, this is 100 hours, so it's now getting very long. And if I go down another 5 degrees, it's going to get longer and longer. And this is the story of the geological age, right? These things are just going out to longer and longer and longer times. And so the intrinsic isotherm, these look like they're non-exponential. And if you just took this information, though, it's insufficient to describe the kinetics of the glass. Okay? Because often some people will take this kind of data and they'll fit it to a KWW function. They'll say, wow. And the beta parameter varies. Not only does the relaxation time vary, but the beta parameter varies. And they say, don't have thermorheological simplicity, for example, or time temperature superposition. But in fact, this experiment, it turns out, isn't sufficient to say that. Okay? All it really tells us is that there's a huge temperature dependence, and it also tells us that there is a non-exponential relaxation. Okay? So, as I said, empirically, the intrinsic isotherms can be described by a stretched exponential with an exponent that depends on the magnitude of the T-jump, such as this kind of KWW function, and indicates a non-exponential decay, but the data set that we have is insufficient to establish definitively that this is the correct way to describe the behavior. Is what? Delta is that volume departure from equilibrium, the V minus V infinity over V infinity. Okay, so now here's the asymmetry of approach, okay? And this is the demonstration of nonlinearity. So again, now what we're going to do is we're going to take and we're going to cool the glass to some point, let's say T1, that's greater than my test temperature. I'm going to cool it into equilibrium at T1. I'm going to let it age or recover into equilibrium. So I start out in equilibrium, and then I'm going to jump down, let's say, 5 degrees. And I'm going to watch it recover. I'm going to compare this with a different T1, with T0 minus 5 degrees, and I'm going to do an up jump and watch it come into equilibrium. If it were a linear process, this would be a mere symmetric result, because everything's happening at 35 degrees. Okay? So, obviously, the term asymmetry sort of suggests that it's not going to be a mirror image. And this is a plot of Kovacs's data, where we plot the departure from equilibrium as a function of the log of the time after the quench. And what we see is in the down jump, we get this kind of behavior. We get quite a fairly rapid. We can see it's almost into equilibrium in 10 to the 4th seconds. And in the up jump, we see that it's quite different. We have not only by the time of just 10 seconds, we have a very big difference in the actual departure from equilibrium. And we find that this is coming and going pretty slowly until it seems to catch up and then reaches equilibrium at a longer time than the down jump experiment. So what people think is happening here is that this is reflective, if you think in terms of free volume, of the material having a lot of space at high excess volume, so the molecules can rattle around and move. And when I did the quench, they very rapidly evolve and then get slower and slower as the density decreases, as the density increases, and come into equilibrium in what looks sort of like an auto-retarded process, is how Kovacs called it. In the up jump experiment, you start off with a deficit of this excess volume, a negative excess volume, so a deficit of volume. So things are crowded and it's moving very slowly to come towards equilibrium. And eventually it starts, as the volume goes up, it starts going faster and faster and then gets into equilibrium in sort of what looks like an autocatalytic process. It's not really autocatalytic, it looks like it on this log plot. Okay? So what's happening? Well, here we think that the relaxation time depends explicitly on the structure of the glass. That means it depends, in this case, on the volume. Okay? So in particular, it depends on the departure from equilibrium in this sense. Okay? So there's a temperature term and there's a structure term. You look like you're getting your...
So I just want to, maybe you're going to say this, but if I didn't want to think in terms of free volume, right, could I just simply say that when I start at the high temperature, my relaxation time is smaller?
Yes.
And that's what's going to show up?
But this curve and this curve are all at 35 degrees.
Right, but the effectively...
Well, this is what people think of as the fictive temperature, right? So this one will have a higher fictive temperature than this one, right?
And the corresponding relaxation time will to a first approximation, tell me how fast it's
right, and when I get to the models, you'll see that they're equivalent, okay? I actually prefer the departure from equilibrium look because I got do a lot of mechanics and it looks like a strain. It's just a volume strain. And so that's actually a very, to me, a very satisfying picture. But a lot of people like the fictive temperature, which is a different measure of the structure. And that's the one that Toole thought of, which had to do with the freezing in of a liquid structure along the glassy line. Right. Yes, Kovacs's line goes parallel to the liquid line, actually. Okay, so that's the asymmetry. And so this is actually what people think. This is demonstration of what's called a material clock, an internal clock, and an internal time, that the relaxation time depends explicitly on this departure from equilibrium or on the fictive temperature. And then the memory experiment. Now this is a two-step experiment, and so you'll have to think about this one. But what Kovacs did was he wanted to see if I worked at this point but got there by different paths, what's going to happen? So first I'm going to define now the fictive temperature in addition to the departure from equilibrium. If I partially age a material and it doesn't get into equilibrium, so that it's always along a line parallel to the glass line, this line parallel to the glass line, where it extrapolates to the liquid line, is called the fictive temperature. Okay? So that's what Sri was talking about of the measure of structure. So this is the fictive temperature. Kovacs's departure from equilibrium is actually along this line. Okay? So what we're going to do is we're going to partially age it and jump up to the fictive temperature, at least approximately. It's hard to capture that. But Kovacs thought I would get here and I'd be at equilibrium. And if I had a simulation time, that's exactly what would happen. It wouldn't remember anything. But when I have multiple relaxation times, what we're going to find is a very interesting set of results. And it's what is called the memory experiment. And here's what we see. This is data. Here's the departure from equilibrium, but the fictive temperature would do the same thing. And what we see is here's a direct jump down to 30 degrees. And here's the memory, depending on, and I don't remember which one is which, how I went through. But the interesting thing is it's non-monotonic, right? So we have a non-monotonic response as the structure changes as a function of time. And this is the memory experiment has to be explained by any model that you're going to have of the kinetics of the glass transition. This is the departure from equilibrium, delta. It was V minus V0 over V0. Okay? But the fictive temperature will do the same thing. It might be the opposite way, but it's, yeah.
So it simply means that the equal volume of this line does not mean equal fictive temperature.
No, equal volume doesn't mean.
Yeah.
Here.
That's
this, right. Yeah. No, fictive temperature formally means
right.
Any place on this line. That's the fictive temperature.
That's right. Okay. But it is not if you go through this line, then it is not thermalized at that condition.
Huh?
It's not in thermal at any time. It was in thermal equilibrium.
Yeah, it's
right?
it's in thermal equilibrium. These are isothermal experiments.
I know, but it's you're just beginning to thermalize, not finished, and never went to the equilibrium state. So anyway.
Well, that has to do though with non-equilibrium process. And can I even measure the temperature? Right. But from this perspective, I mean, actually, these departures from equilibrium are actually pretty small, which is something important to realize. Is you get these very nonlinear effects. I mean, so if this were a compression experiment, it would look like a factor more than 2 difference in the compression and tension moduli. So, and yet the volume changes, here's 1 times 10 to the minus 3, 2 times 10 to the minus 3. Right? So these are for pretty small changes in volume, so not very big departures from equilibrium, and yet you're getting these very large effects. Well, actually, I'm going to talk about that tomorrow. Or Monday, we'll see that there's a lot of evidence that volume is a good parameter. Whether or not it's enthalpy, this is a resort. The enthalpy is a thing. Okay? And there's what these are, and then how do you model them? If I did enthalpy recovery, people that do enthalpy recovery use the fictive temperature. People that do volume recovery tend to use the departure from equilibrium. But you could use a fictive temperature for the volume. And those may not be the enthalpy and the volume fictive temperatures may not be exactly the same. There are some issues like that come in as subtleties, right? Okay, so this is my memory experiment. And so what the Toole-Narayanaswamy, Moynihan, or Kovacs, Aclonis, Hutchinson, and Ramos models do, and maybe I should tell you who these people are. Okay, Toole was actually in the glass division at the National Bureau of Standards back in the 30s and 40s, and did a lot of work, and he was the first one to see the asymmetry of approach, actually. Narayanaswamy, he was a mechanical engineer at Ford Motor Company. Something practical. So Narayanaswamy had a problem with Ford in the late 60s. They're trying to make windshields that are more curved, and they're breaking because the residual stresses in them are wrong. And he developed this model partially to help overcome the problem of residual stresses and cracking windshields. Okay? And Moynihan, of course, is at Rensselaer Polytechnic Institute now as a, well, he's now retired emeritus professor in materials science. And Kovacs was in Strasbourg, but he did his early work on glasses in Paris, actually. That was his Ph.D. work, actually. Aclonis was at University of Southern California. He did sort of a sabbatical with Kovacs, and now he's sailing around the Pacific or landed in New Zealand running a bar or something. John Hutchinson was at Aberdeen. He did a postdoc with Kovacs and is now in Spain. So he's now in Spain, still doing aging and stuff. And Ramos was the smartest one of them all. He's running an oil company in Mexico. So the non-exponential decay, that's what I showed you from either both the memory effect and the intrinsic isotherms. The KAHR model uses a sum of exponentials. The TNM model uses a stretched exponential. The nonlinearity is that the relaxation time depends on structure through what we call time, temperature, structure superposition. So that means that the times themselves depend on the structure, but not the shape of the relaxation. Okay, that's an assumption in the model. One of the reasons they made that assumption was when Kovacs was doing his work, and the same thing I'm sure was true of Narayanaswamy and so on, the computers weren't big enough to even consider a changing shape of the spectrum. But it turns out it's a pretty good approximation. Okay? So the TNM model uses a fictive temperature as a measure of structure. The KAHR model uses a departure from equilibrium delta as the measure of structure. And you need some sort of history dependence, which can describe the memory effect. And they choose that you have Boltzmann superposition for these temperature histories in what they call reduced time or internal time, okay, which is related to this nonlinearity parameter. And I'll show you what the equations look like now. Okay, so here's the constitutive equation. Okay, this is the stimulus-response equation. This is the way Kovacs put it. And I like this. This looks formally like Boltzmann superposition integral. Here's a departure from equilibrium at what's called reduced time, and I'll define that in a moment. It's minus the change in the coefficient of thermal expansion when you're doing volume. If you were doing pressure, you would have to use a change in the compressibility. This is that response function. It could be a stretched exponential or a sum of exponentials. At z minus z prime dz prime dz prime, so this is the convolution integral. This is what we call a fading memory function, actually. And the reduced time, z, is defined this way. Z is a function of just 0 to t of the temperature shift factor times the structure shift factor. And that changes the time scale during the experiment, right? So you have to reduce the time, and it's linear here. But the nonlinearity comes because delta depends upon itself, A delta depends on delta, through the reduced time. So that's the nonlinearity. Okay, so that's, I'm sorry?
How do you define A, T, and A delta?
I'll go to that, but this is a temperature shift factor. You could use something like a WLF or Fogel-Fulcher temperature shift factor. Generally, the TNM model, they use a activated process, but just a apparent activation energy. So, and this is what the reduced time is defined as for the TNM model. It's still AT, so a temperature shift factor and a structure shift factor. The details of these will not be the same in form, but mathematically these turn out to be the same models, okay? And here's the different relaxation functions. The Kovacs like to use a sum of exponentials. It's more versatile, at least, because you're not stuck with having to use this. But this is what the TNM people use, and this is a reasonably good approximation in most instances. And here's the temperature functions you asked about. So this is the time divided by a reference time. So the time, relaxation time at a temperature and a given departure from equilibrium. And there'd be a reference condition, which would be some temperature in equilibrium, and where delta is 0. So it looks like this. And then Kovacs had it equal to e to the minus theta, t minus t reference, and then e to the minus 1 minus x times theta delta over delta alpha, where theta has the role of something like an activation energy, but it's really related. Down here I say he has an EA as RTG squared. Okay? And the x is called the nonlinearity parameter, and that's related to how you partition the response between delta and just temperature. Okay, so that's how Kovacs did it. In the case of the TNM model, they do it in terms of the fictive temperature, but then they use an activation energy, this delta H over R, and x partitions things, and it's clearer here when x is 0, there's no temperature dependence, it's all fictive temperature dependence, and when it's 1, it's all temperature and no fictive temperature dependence, okay? No structure dependence. And so this is, well, yeah, but, you know, there's been a lot of work done. This is how they originally did it. People have put in Adam Gibbs, and so forth, so there's a lot of different ways to deal with it. Usually in these experiments, because the time scales are so long, you're over such a limited temperature range that it really doesn't make any difference, okay, from a practical point of view. But I agree, it would be better if this had been originally written as something like a Fogel-Fulcher or WLF expression, at least at the time we were doing that. That's what people think.
The justification for the KAHR expression is less clear.
Oh, no, I mean, it's just the way that you partition the temperature. Now, the thing is, it's more complicated in the KAHR form because there's a temperature factor in 2 places, and it partitions it a little bit differently because of that, the difference in the definition of structure, right? So, but these can be made equivalent. It's not a problem. Okay, they're mathematically equivalent. It's just a construction. Okay. In fact, one of the problems with these is you'll notice they're totally empirical, right? You know, and that's a philosophical view. The thing is getting something better is the challenge. You know, and people have been working on these for over 30 years, actually. So, and this just shows the TNM. TNM has an advantage. They like to cast it in a differential form, and it's easier to do your computer simulations if you do that. But it's equivalent again to the Kovacs form. Whoops. Okay, and I just, as an operational definition, determination of the fictive temperature, usually we don't measure enthalpy directly. We don't get the enthalpy surface. We measure heat capacity or apparent heat capacity. So if you do a DSC scan, what you have to do is you have to construct the, this is from Moynihan, the hatched area has to equal the area in the lines. So I'm sorry, the area here has to equal this area plus this area. So they're equal, and then you get the fictive temperature. But it's the same definition. One of the things about, of course, doing enthalpy measurements is the enthalpy surface isn't such straight lines as the volume surface. So then we want to ask, well, how well do these models work? Okay, well, I'm going to show how well they reproduce this asymmetry of approach. Well, yeah, I mean, if I have let's go back. I mean, that's just a geometric construction of the derivatives of this thing, right? And getting that intersection point from the heat capacity, because the heat capacity is the slope of these curves, right? Okay, so that's Moynihan's method of doing it. So you have to take, and it turns out geometrically, when this area and this area equals this area, then you get the fictive temperature. So, okay, so what we want to know is how well do these models reproduce the experiments, the cataloged experiments that Kovacs did, and can we reproduce the asymmetry of approach? They reproduce the memory or crossover effect. And as a practical matter, it also captures that enthalpy overshoot in the DSC measurements, which is actually a very important thing because early on, and there's a history to this, right? Early on, people were doing things like they'd see these large excess enthalpy peaks, and they were saying, oh, it's a first-order phase transition. Well, that was the kinetics going on. And these models capture that sort of thing, and I'll show you what that is. So, okay, so here's the DSC experiment. So this curve, the solid line here, is without any aging or structural recovery. Okay, this is one where there was structural recovery partially, and you can see you're starting to get this big excess enthalpy. And as you age it more, you get an even bigger peak. And the dashed lines are the fits to the data. So what you see is that you actually, the model captures pretty well that behavior. Not perfectly, though, so this is actually still a challenge. We don't actually fully understand what some of these deviations are. Okay. For the asymmetry of approach, you have to compare this curve with this one, because that's the 5-degree temperature jump, because the temperature is at 140. This one's at 100. So and then you compare this one with this one. But what you see is it captures pretty well the asymmetry of approach. And this is for polycarbonate on our own data. So that's good. It captures the nonlinearity, at least at those two sets of temperatures, or three sets of temperatures. And this is our attempt to predict Kovacs' memory effect from asymmetry of approach fitting parameters. Okay, so now we see we qualitatively capture what's going on, but we don't quantitatively get it, right? There's some issues here. And the thing is, right now, this is the best, really the best we have available for fitting or characterizing or predicting the behaviors. So we know we need a sum of exponentials. We know we need Boltzmann superposition of some sort. We know we need this nonlinearity type behavior, the time structure superposition. But beyond that, I remember in 1990, the first meeting on relaxations and complex systems, we had a big one of these discussion sessions on why don't these models quite work. And people had all sorts of reasons, and people have gone off and tried to fix the models. They still haven't come up with anything better. So actually, from a theoretical point of view, there is a real need. I mean, from a practical point of view, there's a real need for better models. I think that the closest thing to an attempt to give a better model is Jim Carruthers' group from Purdue University has taken and used rational mechanics approach to try to capture this from a more fundamental point of view. It's not so empirical. It's phenomenological, but it's not empirical like this. And while he can capture a lot more behaviors, his description of this kind of thing isn't very much better than what we get out of the TNM and KAHR models, but it's at the cost of a huge investment in computational capacity. So the models are good representations of the kinetics of structural recovery, but they don't capture all behaviors. Material parameters can change as temperature range changes. So if I go outside that sort of narrow window, and I go, let's say, if I fit data in about a 15-degree temperature range, if I go to 20 degrees, 30-degree temperature range, what I find is the parameters change. The models, the parameters are not changing. Okay, so that's actually an important thing. When we go to deep quenches, these are the so-called sometimes hyper quenches, what we find is that the models virtually break down completely. And there's a little bit of work going on in, I guess, Denmark at Aalborg, but I think that there's some problems with some of that. But people are trying to do that, and they're also not fixing up this problem at the same time. So it's just sort of semi-empirical again. Actually doing pressure jumps are a problem. Okay, O'Reilly and Turbone and others have tried doing pressure jump experiments, and they look just like the other ones. You know, they sort of fit, but they sort of don't fit. So that's an issue. Unfortunately, I guess I have to say, these models are the current paradigm for describing structural recovery. They capture sort of the main ideas, but they don't really capture everything that we know happens phenomenologically. So the experiments are well ahead of this. And the thing is, like I said, that discussion went on in the 1990s, early 90s, and in fact, really no progress has been made since then. It's a really complicated problem. Okay, it may require some issue of looking at the details of whatever we want to call state, structure, heterogeneity. It may be that it requires something like that. Okay, so I wanted to share with you another thing we did, and this is what I call another path of structural recovery. And these are experiments made possible by a plasticizing effect in polymers. What is plasticization? So, according to free volume or configurational entropy models of the glass transition, addition of small molecules that have a low glass transition to a polymer leads to a decrease in the TG of the mixture. Okay, so that's the first point. So I can change TG by changing composition. If the small molecules are volatile, we can take advantage to rapidly dry the sample through the concentration glass transition and search for the same signatures as when one changes temperature rapidly. Okay? In what follows, it's shown that the glasses subject to such chemical activity or plasticizer jumps are only qualitatively like temperature glasses, another strong instance of the path dependence of the glassy structure. So I'll show you what I mean, and we're really going to see that jumping out of a plasticizing environment creates a glass that has different properties than if I go to the same place jumping through out of temperature. So this is something that the theories also have to capture. And so, but here's an example of plasticization. This is a polyalpha-methylstyrene polymer, the heat capacity versus temperature at different concentrations. Here's 100% polymer, so you see TG is up here greater than 440 degrees. And this is the pentamer. Down here, the TG is only about 260 degrees or something like that, okay? And actually, it's interesting, the equilibrium curve is independent of concentration, okay? But you don't have to worry about that for now. But this just shows, so I can actually imagine doing something like with this, where I would put in a little bit of this, and I'd change TG, okay? And then I can, if this were volatile, which it's not that volatile, if it were volatile, then I could just change pressure, and I could jump the glass transition. This is another example. This is another example of plasticization. This is the TG as a function of weight fraction of different solvents in polymers. And of course, it's very important in polymers because if you use polymers and are subjected to a plasticizing environment, like water everywhere, it can be a problem in their performance. So your airplane wings made out of epoxy, the TG, you know, is affected by water. It's affected by those cleaning solvents that the airlines use, or de-icing solvents and things like that. So these are actually very important practical problems too. But so we can see in this case we have a TG change of like about 140 or 150 degrees or something. And it's the biggest there we have, depending on the solvent in that case. So okay, so here's the idea. If we look at the volume versus temperature at different relative humidities, because it's hard to control plasticizer content, but we can control relative humidity. The idea is I jump from my equilibrium state down to a lower relative humidity, and then I'm going to watch the structure change. And I'm going to ask, can I do the same things I did with temperature? So the original hypothesis we have was that I should be able to construct a volume, relative humidity, temperature surface. And if I get to, let's say, this non-equilibrium place, it doesn't make any difference whether I came from up here or I came from down here. I should get the same behavior, right? If let's say, free volume were the correct idea, and this were something related to the free volume, then I would get here, and then I should get the same response, and I should be able to model it with the same parameters between the temperature jump and the plasticizer jump experiment. So the change of relative humidity, and we also ended up doing some CO2, carbon dioxide, because that's also important, has a similar effect to temperature changes on the structural recovery and physical aging. So I'll talk about physical aging Monday, but I'll talk here, I'm going to talk about this. So again, remind you, this is the intrinsic isotherm experiment. In the case of the plasticizer jump, I won't do a jump in temperature, I'll do a jump in chemical activity, which is a vapor pressure, and I'm going to call that an intrinsic isopiestic instead of an intrinsic isotherm, but conceptually it's the same thing. I should be able to do experiments now where this would be volume and this could be against concentration, and I should be able to get an asymmetry behavior. And can I also get then this kind of memory effect if I do the right partial structural recovery experiment and jump up to a fictive concentration, not a fictive temperature, of course. And I want to compare them. So we built an apparatus to do this. We use thin films so the diffusion time isn't too long. And so we want to ask if we can get these. And of course, we also then want to compare the intrinsic isopiestic, intrinsic isotherms directly, and we're going to show some anomalous kinetics. I'm also going to show some anomalous behavior in the what I call a volume overshoot. So something to be explained at least. So the volume measurements, we're going to, turns out these are thin films, I can't put them in a dilatometer, so I'm going to measure length change. But we chose our polymer so it had a solid structure because it's cross-linked. It's isotropic. The volume changes based on length. And because of the way we do it, we have to straighten the film. There's a very small stress on the sample as we do it. And here's an example of a volume normalized to some reference volume as a function of relative humidity now as we dehumidify the sample, okay? And we get something, an alpha, which is now related to relative humidity instead of temperature, for example. And we would have a delta alpha related to relative humidity instead of temperature. And we have a relative humidity glass transition of about 66% under these conditions, which were something like 2% change of relative humidity per minute. And lo and behold, when we do the jump, we see just like what we saw with temperature, we see intrinsic isopiestic now. So, and these are getting longer as I go from, in this case, 90% to 60%. At 60%, it relaxes faster than it does at 30% relative humidity. So it's just like I lowered the temperature. And this is the same kind of experiment, but now it's at 65 degrees instead of 60 degrees. And again, the volume departure against log time. And again, we see it comes faster, slower, slower, and slower as I reduce the final relative humidity. So the intrinsic isopiestic looks very similar, at least qualitatively, to the intrinsic isotherm. When I do the partial structural recovery, so this is the direct jump to 50% from 90% relative humidity. Then I do this two-step from the initial relative humidity of 90% down to 30%, let it age for some time, and then jump back up to 50%. I find that I get this curve. And when I do it at 40%, I get this curve. And when I change temperatures, I get qualitatively the same thing, but I'm getting the same kind of response. So I get the memory effect. Well, this actually also has some practical implications because in composite materials, people will characterize their polymeric resin by putting the sample in water, and then they'll watch a mass change, okay? And they'll say, if I change mass, I've been leaching things out. But in fact, they might be seeing something like this, which means that they didn't leach anything out. All they had was some sort of memory effect in their experiment. So it's actually something to be aware of from a practical point of view as well. And then we also get an asymmetry of approach. Okay, so you can see it's not quite as strong as when we did the temperature jumps. Okay, the asymmetry, so the nonlinearity here isn't quite as strong apparently. And I just want to show this. We know when we do jumps from different temperatures to the same temperature below TG, and we look at the volume departure versus log time, we know that eventually these things merge at long times because it looks like a fading memory process. Okay? Well, we see here when we go from 90% to 50% and 65% to 50%, we get this merging at long times. Okay? So that's what you expect from a viscoelastic response at the same final condition, in this case 50% and 60 degrees. Okay? So now what happens though if I jump to say 50% and 60 degrees, but I do it both along a humidity path and from a temperature path where I started at 50% relative humidity. So I can do that. And what we see was a great surprise to us. So here's from 90% to 50% at 60 degrees centigrade versus 75 degrees centigrade to 60 degrees centigrade at 50%. So we're same final relative humidity, same final temperature. So the final external variables are the same. And yet, here's the temperature jump. Not only do we have a smaller volume departure from equilibrium, but we also have a faster relaxation into equilibrium. So, and here's the humidity jump. It seems to have a much longer time, maybe up to a decade. Here it's even more than a decade in this case, for the volume recovery into equilibrium. So that was the first hint that maybe there's something different about the humidity-created glass compared to the temperature-created glass. So I said, we know it's path-dependent. We didn't know that this would lead to it. It also is, in any simple fashion, quite contrary to the ideas of free volume. Because here I have a higher free volume, and yet it's relaxing more slowly. Okay? So that's actually a difficulty for free volume models. I expect it's probably a difficulty for enthalpy models too. So we also tried to fit the data using the TNM-KAHR model type of behavior, and instead of using temperature, we extended it to relative humidity by replacing the temperatures with and activation energies with relative humidities, an activation type parameter, but that's related to relative humidity effects on the mobility and the delta alpha RH. And it turns out the fits were sort of about the same as if you did it for a temperature jump. So I'm not going to show the details of that. But they were sort of about as good. But the parameters were really different. Okay? Because why? The relaxation times are looking different and the dependencies are different. So it's actually looking different. And the thing that was really surprising, if we normalize these to the same departure from equilibrium, so the same amount that you're away from equilibrium at a given temperature, so this is 60% relative, 60 degrees centigrade and 50% relative humidity. When I do the down jump experiment, the red is the temperature jumps. In the case of the temperature jump, the relaxation times are much faster than in the humidity jump. So this is the relaxation times required to fit the TNM type model to the structural recovery. But then as we go through 0, that's the equilibrium point. So this would be equilibrium. Fortunately, they cross, so we don't have a problem there. But now, when we're on the other side, since these lines continue, now when I'm in a deficit of volume, it turns out now my relative humidity experiment has a faster relaxation time than my temperature experiment, and that's why I have a lower asymmetry. Okay, so here they're slower, and here they're faster, so I have a lower asymmetry of approach. Okay, so we also able to do this at carbon dioxide pressure. We just had to do what we had done before with a pressure vessel that shows the pressure vessel. So we do a lot of experiments. And the reason we were interested in this was not only what we had seen, but there's been some work by Behrens and Hodge where they actually took particles of polyvinyl chloride polymer, and what they would do is they would expose them to a vapor and then jump the vapor, and then they would do enthalpy recovery experiments. Okay, and this was the kind of graph they made, which I'm not sure I totally agree with this graph, but this was what they said was happening when you hyperquench a glass. It comes down, it recovers quickly, and then when you heat it, it does something funny like that, where this is the normal glass, where you heat it, and then you come up and you get this overshoot, and that's the enthalpy overshoot. And so why does the first why does what? This one? Yeah, that's what I don't agree with. I don't think it does that. Yeah. We just took this right from their picture, you know, and we don't think this is what's happening anyway, but so they had something funny. So, yeah, we should probably redraw that picture, I guess. But anyway, but in any event, both hyperquench and the carbon dioxide quench have excess volume. And so the question we wanted to ask was, is our behavior similar to what they reported? And actually what we found was very different, and it's consistent with what we found with the humidity jump experiments, because the relaxation times are for a given volume are too long. So here's what we did. We do a carbon dioxide pressure jump, and we create something with an excess volume compared to the sort of normal glass behavior. And what we see is that it sustains that volume up to actually almost 80 degrees centigrade, where the TG is below 70. It sustains that volume and then collapses as we heat it. And then it comes back down, and it's on this glass line. So the glass created by the PCO2 jump is different from that created by the temperature jump. And that's just what we saw with the humidity jump experiment. So it's more stable. So this is a route to making glass more stable, but with higher volume, which is really contrary to anything we expected. We never thought that. But it shows, again, this creation of glasses of complex structure is really very, very path dependent. Okay? We chose a plasticizer path because it makes sense in the context of polymers. We can do that. But it also implies, and we know that one of the problems with pressure jump experiments, in polymers at least, is that if people form glasses under high pressure and then release the pressure at room temperature, they have a densified glass, something that's quite dense, but the relaxation times, even though you have a higher density, are almost the same as if you had just done a normal cooling and gotten a glass with a higher free volume. Okay? So in fact, there's some subtleties in the path dependence that is not at all captured in these models of what I just described. So again, and it's a challenge, I think, for the theoretical community to think about these things, because this is the ultimate goal, is to be able to explain not only the glass approach to the glass in the equilibrium liquid, but what's happening actually in the glassy state. Because why? Well, if these things are all changing and I'm trying to predict behaviors as an engineer, we want to know how to predict those behaviors so we can predict what? Long time performance of materials. If somebody puts a polymer gas pipe in your backyard and they tell you it's going to last 100 years, okay, well, that guy's not going to be around in 100 years, right? You don't want the gas pipe blowing up for other than the backhoe going over it, right? So it's very important long-term issue. So anyway, so here's what we said is happening in the PCO2 created glass compared to either the hyperquench or the normal glass. So it's higher volume, but it also seems to have a wrong behavior for having all that excess volume. Okay, I'm going to skip this because we get the same results when we specifically do, but it is nice we can show enthalpy recovery. We did it in terms of delta, but we show a memory effect also in the enthalpy, okay, for carbon dioxide. Oops, why did it go back? Okay, So, okay, so the last thing I want to talk about is what's happening at the nanoscale. Okay, so structural recovery at the nanometer size scale is something that people are interested in TG at the nanoscale, what happens. And what we had done was we took orthoterphenyl, it's a sort of ubiquitous glass former. We imbibed it into these control pore glass beads, which have pores somewhere between, well, we went all the way down to 4 nanometers, but 11, 25, and 50 nanometers about. And here's what we see. Here's the typical behavior, okay? This is the bulk normalized heat capacity, so you can see as you age it, this big buildup in the excess enthalpy. Whereas when we put it into a pore, and this is the 11 nanometer pore, I'm sorry I don't have it on there, we see that it looks like the enthalpy is building up much less. Okay? So the question is the aging rate slowing down, or is there something else going on? I mean, our original, we had done some work back in the 90s thinking that this was slowed down aging in the nanopores. But we now don't think that's the case, and here's the reason why. So now here's the fictive temperature as a function of aging time for the materials confined to pores. So the key to fictive temperature is that if I age at a given annealing time, the fictive temperature should reduce to the annealing temperature. That would be 0 departure from equilibrium. And what we found when we put the material into the pores is it wasn't doing that. It was going somewhere else. So here's the bulk. It's coming down to 0, TF minus annealing temperature, the fictive temperature minus the annealing temperature. But in the pores, it looks like it's coming off to some other state. Well, imagine you have your material, orthoterphenyl, is inside a cylinder. Really, it's a pore, but there's cylinders. And it sticks to the wall. Now it can't change volume. So we have a change from an isobaric condition to an isochoric condition. And the question is, where does that change occur? Is it occurring at high temperature? Or is it occurring at, it turns out, in these experiments, the glass transition is also observed to be reduced in the nanopore. Okay, so you put the orthoterphenyl in the nanopore, and the TG goes down. So what we thought was, well, maybe if we have isobaric or isochoric behavior, we're going to have differences in enthalpy. So here's the equilibrium line for the isobaric condition. Here's the equilibrium line for the isochoric condition. And then this is what happens if we did the vitrification at the different points. Okay? So you have different enthalpies. So this is the definition of the differences in enthalpies, CPL minus CVL, okay, here, at TF measured minus TA, okay. And I just remind you that we actually know that we can get glass formation in the isochoric state. And what we did was we recast the bulk structural recovery in terms of, for the TNM model in terms of delta, because why? We now have a mixed problem of going from isobaric to isochoric. We really need a better measure than the fictive temperature and fictive pressure. We just used the departure from equilibrium, and we cast it this way, so we can do that. And then we can calculate, and we see that the TNM model describes the structural recovery for the bulk material at different distances from the glass transition, TG minus different amounts. And so we had to do it for isochoric aging and subsequent to return to 1 atmosphere as we go through whatever the glass transition is, okay? And so these are the terms. This is the definition of the log tau, and we now have also a pressure term in addition to the temperature terms. And here we have P0 is some P ref times alpha G, Kg is the bulk modulus in the glassy state times the change in temperature. And the equilibrium pressure is the reference plus alpha liquid, K liquid times delta T. And TF minus TA then looks like this. It's delta H over delta CP. And then we have the CPL minus CVL term, delta T plus delta over delta CP. And this is the reason why TF minus TA does not go to 0, as I showed on the schematic. as the departure from equilibrium goes to 0. So the assumptions we used to model this aging were the model parameters describing the bulk recovery should describe the recovery in the nanopores. That's the assumption. We now have 2 additional adjustable model parameters. One is this theta P, which is the pressure dependence of the relaxation times. And then, and this is the key one, the T of the constraint, well, it turns out it's going to be approximately equal to TG in the nanopore. But this is a floater. This is what we found is that's what it is. Okay, so it was a fitting parameter. And the values of the material parameter, all the other ones, all these values are obtained from the literature. Okay, and so we made 2 other assumptions to see if it made a difference. We assumed either pressure relaxation is instantaneous or that it relaxes at the same rate as the enthalpy. Of course, the pressure might relax at a different rate, but this is two limits. And you can see it doesn't make very much difference. What we see is that we fit reasonably well the data. We describe the data. And the important thing of the fitting parameter here is that the TG in the constrained system turns out to be equal to the TG in this particular, in the 50 nanometer pore, that we measured in the pore. And then in the case of the next size pore, the 25 nanometer pores, it turns out within 2.5 degrees, and we see again we have very good description of this recovery to something that looks like an isochoric state. And these are the parameters we used. And I think I'm going to stop because I think I'm past time. And acknowledge the people and I had a lot of discussions with, and also the people who gave money. And with that, I'll be happy to answer any questions. Thanks.
The material goes to the same state to which it would have been if the quenching was not done. I mean that the material glass reaches the equilibrium line on structural recovery.
The structural recovery will go to the equilibrium line, yes.
It exactly touches that equilibrium line, or there is some...
Okay, Kovacs did a lot of work to try and look to see does the volume recovery go to the extrapolated equilibrium volume line, and it does, yes.
Okay.
Yeah.
And what is actually happening in the structure during the structural recovery?
That's a good question. It's getting closer to equilibrium.
Yeah.
Well, I think that's sort of the question that everybody's asking, right? Is if you think it's the fictive temperature, what it's doing is it's sampling different liquid states, right? Liquid structures. If you think it's a volume departure from equilibrium, then you think that, remember, these are small volume changes. So you don't really need very big molecular rearrangements to accommodate a strain of 10 to the minus 3, right? So I think that probably not very much is happening. But if you're close to some really point where packing is very important, which is where TG is happening, right? Where if you read Ferry thinks that the TG occurs when the free volume is 2.5%. So if you have small changes in free volume around 2.5%, and relaxation times that are getting very long, then it's just small changes in the packing that lead to large increases in the, or decreases, depending on if I'm expanding or contracting, in the relaxation time. Right?
But the free volume is enough to explain the relaxation, or there are some other processes also going on during the structural recovery?
Well, yeah, because certainly the enthalpy is changing, and so the entropy is changing. And if you want it to be entropy, then we'll have to argue about entropy. But again, it's subtle differences, right? It's small differences. It's not very large differences, right?
Mentioned about this TG variation in different measurement techniques. Why?
Why?
Why it is happening?
Well, one is that, okay, if I look at the dynamic response of the material, it's frequency dependent. So for one, if I do just something at different frequencies, I can get a difference in TG. Okay, so then somebody who does a dynamic mechanical measurement might do it, or a dielectric measurement might do it at 10 hertz, and that's faster than the normal, say, DSC scan. But also, even within the mechanical experiment, if I define my TG as the peak in G double prime or the peak in the tangent delta, okay, the storage modulus or the ratio of the storage modulus to the this tangent delta is the ratio of the loss modulus to the storage modulus, or the peak in the loss modulus. Those occur at different places, and they're about 30 degrees apart. And that's a question of definition. Okay, so, but that's the point, is that because TG is dynamic or kinetic, you have to worry about the definition that you're going to use for your TG. A lot of people like DSC. The DSC doesn't vary very much. If you do it dilatometrically, it's similar, but not necessarily identical to the DSC. And then when you go to, but there are some materials that have very low heat capacity changes at the glass transition. In fact, some are so low that you can't see them in your DSC, particularly in polymers. And so what you find is if you change temperature and do a dynamic mechanical or dielectric experiment, you still have enough sensitivity to see the changes in molecular mobility that occur around TG, but those show up at different points than just related to the heating or cooling rate alone. Okay, does that make sense? And if you want, we can talk about it a little bit later because it might take some. Yeah.
Apart from this frequency dependency that you have told, like if I take a thin film of a polymer and I'm doing measuring the glass transition using ellipsometer or reflectivity, I'm using same frequency, like the cooling rate, the heating rate is same, but people are seeing different results in these two techniques for the same polymer film with same thickness.
Okay, so this was ellipsometry versus?
Ellipsometry versus X-ray reflectivity.
Oh, yeah. The nanoscale TG question is one that is really a bag of worms, because it seems like some people actually do the same measurements and don't get the same answer, right? So I think there's a lot of questions about exactly what's happening at the nanoscale, because there's a lot of issues of surface, and people really don't know. The models we have, if we were to use entropy models or free volume models, don't readily predict any of what's happening, so I think that yeah, ellipsometry ought to look like dilatometry, right? Yeah.
As you started speaking about the surface, like, can you just say about what is surface glass transition?
Do I believe in a surface glass transition? There's been some work lately that's actually very clever. Thackeray and Forrest did some work where they were actually embedded a bead in the surface at above TG, and then they go below TG, and it was a gold bead, and so then they dissolved it away with mercury. And then they watched the surface recover after they dissolve it away. And the apparent surface relaxation times in those instances are just too fast to be a glass. And they don't see any evidence of glassiness. They just see a fast relaxation, right? So from that perspective, it doesn't look like there's a true surface glass transition. It might be it's related to being the surface is a very high fictive temperature. But even when they get down to pretty far below TG, a couple hundred degrees, they still see this rapid dynamics. So they don't see a switch over to the slower dynamics. It's also not a stretched exponential. It's a single exponential decay. So again, that gets away from the complexity. So the surface seems to be behaving more simply, unless it's constrained. So if you put the gold bead on the surface and watch it go in, you can describe that by the macroscopic rheological properties. So then it looks glassy.
So surface glass transition, can I say that it doesn't change peak temperature from the how far it is from the interface of the substrate and the film?
Okay, so you want to repeat that?
So how much extent we can say that it is kinetically active? Means, is it saturates if I do cooling rate enough slow cooling rate and heating rates? Is it saturates or?
Okay, DSC or any experiment, actually, if you really want to measure TG correctly, you have to take the TG on cooling. And when you do DSC, the reason people don't like to do that, there's two reasons. One is it's very smeared out, so it's hard to see the TG change. The other is there are not very many standards for calibrating a DSC on cooling, okay, because of supercooling of the crystal. But usually what you'll do then is you'll get the limiting fictive temperature. So you'll cool at some rate and heat at least that rate, and then calculate the fictive temperature using Moynihan's method. That's called the limiting fictive temperature, and that's within a degree of the actual glass transition when people take the midpoint or something like that. So that's how you should do it, and then it's rate dependent. It's not heating rate dependent, though. That's the mistake people make. The TG is not heating rate dependent. Okay, the peaks in your overshoots and things like that are heating rate dependent, but those aren't what the fictive temperature is. So you have to be a little careful, but they are cooling rate dependent. And the cooling rate dependence is the same as what I mentioned about 3 to 5 degrees per logarithmic decade of rate.
So one more question. So structural recovery won't be homogeneous everywhere. Means while aging also, it will be one where it will be more recovered, and one way someplace it will be less recovered. Why it will be?
I guess I didn't understand the question. Right.
So structural recovery won't be homogeneous.
What won't be homogeneous?
In some systems.
The structural recovery. Yeah, but that's what people are debating, right? Is how heterogeneous or homogeneous is the glass structure itself, right? But they're very small subtleties. I mean, if you take and do scattering measurements on a material as it samples fictive temperature space, it looks like the liquid at the higher temperature. It isn't as if your heterogeneities were making huge changes. Well, I can't answer about the heterogeneity. That's going to be a philosophical
debate
later
on. So before you go, very important announcement about. Let's thank Greg first.